Today, we are going to pull back the curtain on a core idea in statistics that you see in headlines every single day. But, well, it's almost always misunderstood. We're talking about statistical significance.
You've seen these, right? Headlines just like this one. They pop up everywhere, they're super exciting, and they're almost always based on some study that found a significant result. But what does that word significant actually mean when scientists use it? And here's the problem. Those headlines can be really confusing, or worse, totally misleading. It's a classic case of statistics gone wrong, because getting from the data to the headline is a tricky business, and a lot can get lost in translation. Now, if you're someone who feels their eyes glaze over when they see charts and numbers, you are in very good company. Researchers actually have a name for it: statistics anxiety. It's a real thing. But stick with me, because we're about to turn that anxiety into confidence. The good news is, experts have already mapped out all the common traps people fall into when they're trying to understand data. Think of them as the classic tripwires of statistical interpretation.
Here's a list of 9 of those big mistakes. Everything from bad analysis to, just getting way too excited about the results. Now, for today, we're going to do a deep dive into what might be the most important one of them all. Number 2.
Yup, we're zeroing in right here. Because honestly, if you can get a solid grip on these 3 things, hypothesis testing, p-values, and significance, you are going to become a much, much sharper critical thinker, no matter what data you're looking at.
So, how do scientists test an idea in the first place? Well, they don't just guess. They use a really structured process called hypothesis testing. The best way to think about it is like the scientific method, but built specifically for data. It's how we separate a real effect from just random noise. Every test begins with something called the null hypothesis. Now, the easiest way to wrap your head around this is to think of the legal system innocent until proven guilty. The null hypothesis is the innocent part. It's the boring default assumption that there's nothing going on. No effect, no difference. The coffee does absolutely nothing. That's our starting line. And then you've got the alternative hypothesis. This is the new, exciting idea that's on trial. It's the claim the researcher is actually interested in, that there is an effect. The new drug works. The coffee is linked to a longer life. This is what we're hoping to find evidence for. And the whole thing follows this simple 5-step recipe. You state your 2 competing ideas, you go get your data, you run the numbers, you make a decision based on what you see, and then you share your findings. It's a super logical flow from a question to a conclusion. Okay, so now we get to the heart of the matter, the key piece of evidence that the statistical test spits out. It's called the p-value, and it is probably the single most powerful and yet most misunderstood number in all of science. So what is it really? A p-value answers a very specific question. It asks, if the null hypothesis, the no effect idea, was actually true, what's the probability we'd see the results we saw in our study just by pure random chance? So a tiny p-value means your data looks really, really surprising if you assume there's no effect. Now listen up, because this is the part everybody gets wrong. A p-value is not the probability that your idea is wrong. It's not the probability that your results were a fluke, not at all. Think of it as a surprise meter. It just tells you how surprising your data is, assuming that boring, no-effect story is true. So here's how it works in practice. Before a study even starts, scientists set a cutoff line, usually at 0.05. If the p-value from their test comes in below that line, they get to declare the result statistically significant. And that gives them strong enough evidence to reject that initial no-effect idea. But notice the language. We're not proving our idea is right. We're just rejecting the other one. And that is such a key distinction. Statistics isn't about absolute proof. It never is. It's about evidence. We never say our theory is 100% true. We just say, you know what? The evidence makes that no-effect story look really, really unlikely. Okay, this brings us to the final, and I would argue the most important piece of this whole puzzle. Just because a result is statistically significant doesn't automatically mean it's actually important in the real world. Let me be as clear as I possibly can be on this. Statistical significance is not the same thing as practical significance. They are 2 totally different ideas, and confusing them is probably the biggest data mistake you can make. Think of it like this. Statistical significance just says, hey, the effect we're seeing is probably real. It's not just random noise. But practical significance asks, okay, cool, it's real. But is the effect big enough to actually matter?
I mean, with a giant study, you could prove a pill lowers blood pressure, but by an amount so tiny it would make zero difference to anyone's health.
So, after all that, what's the big takeaway here? What's the one thing you really need to remember? Let's bring it all home. I think this quote from Simply Psychology just says it all. A p-value is a tool. It's a really important piece of evidence, for sure. But it is not the judge and jury. It's just one clue that has to be looked at with everything else, like how big the effect is and whether the study was any good in the first place. So I'm going to leave you with this. The next time you see one of those breathless headlines about a significant new finding, you'll be able to see right through the hype. And you'll know to ask the single most important question. Okay, the data shows there's a difference. But is it a difference that actually makes a difference?